this is Twitter Thing. Thank you for joining me here. My name is Daniel. To those of you who have not seen me before, if this is your first time, then this is my face. Okay. Anyway, so I want to start a new series with you guys. We are going to talk about network analysis, the course network analysis, or probably network theorems. Let me put it that way. The first thing that you need to know is that we need to understand what we mean by the Kirchhoff's voltage and current laws. Once we get that, it will be easy for me to start complex calculations with you under various topics, okay? Now, when we say current divider rule, what does this mean? So I'll break it down for you to understand. Now, the current divider rule states that in a parallel circuit, the current entering through each branch is inversely proportional to the resistance of that branch. And it is directly proportional to the total current entering that branch. Or another way you can also define it is that the current entering through each branch of a parallel circuit is directly proportional, this time not inverse, okay, directly proportional to the conductance of that branch. Now, remember that the conductance is the reciprocal of the resistance. So you can read about conductance and resistance, okay? Now, resistance is measured in ohms, conductance is measured in Siemens, okay? So when you read further, you will understand. Now, there is a formula for the current divider rule, and I need to teach you to understand it so that when I'm applying that in complex calculation, you know what we are doing. So now look at this diagram on the board. I have a 15 amps, which is my total current, entering into this branch. Then some will split and enter into branch 2. Now, the current divider rule says that if I want to find the current passing through branch 1 or branch 2, I need to apply a certain formula. Now, let's see what will happen. Let us label the branches here. Let's assume that this is R1, resistor 1, and this is what? R2, okay? And this current, which is passing through R1 and R2, will move in this direction, okay? To move in this direction. Let us call this current IT, which is known as the what? The total current. Now, the next thing we will do is that when IT reaches this node or this junction, it will split into 2 using Kirchhoff's current laws. One will pass here. Let's label that one I1. One will also pass here from here. Let's label this one I2. Now, do we get the concept? Very good. Now, if I want to find the current that is passing through this side, which is branch 1, how do I find it? According to the formula, it says that the current that is entering through this side is inversely proportional to the resistance of this branch. If something is inversely proportional, then it means that as this one is increasing, this one is what? Reducing. Now watch. So if I want to find I1, I'll quote my formula by writing my I1, which is equal to, current divider rule says that the first thing you need to do is to take the total current, IT. Use it to multiply the opposite resistor. Why am I saying that? Because this current is inversely proportional to this. So I do not need to use it to multiply this. So I'll multiply the opposite resistor. The one that I1 is not supposed to pass through, or the one that I1 is not passing through. So I'll write my what? R2. Divide the result by R1 plus what? R2. You could see that this I1 is inversely proportional to this. As this one is increasing, this one is what? Reducing. The value of this one is reducing. But it is directly proportional to the resistor value or to the resistor that I1 is not passing through. Are you here with me? So you can see that this R2 is directly proportional to what? The I1. In the same way, current divider rule says that if I want to find the current through the second branch, which is I2, what do? I'll just write my I2 equal to the total current times. Now, where is I2 passing? It is passing through R2, the second resistor we have here. I will not use that one, but I will look for its opposite resistor, which is what? R1. Write it here. Divide the result by the same R1 plus what? R2. Are you getting the concept? This is what the definition was saying, that the current that is entering through that branch will be inversely proportional to the resistance of that branch. What is the resistance of branch 2? It is what? R2. And you can see that it is inversely proportional and directly proportional to R1, and also directly proportional to the total current entering the branch. Where is the total current? Look at it. That was why in the definition I said that it is directly proportional to the total current entering the branch. So you could see I1 is also directly proportional to the total current. Now, if I am able to find I1, I don't even need to use this formula to find I2. Then I can use the Kirchhoff's current law to generate the second value for what? I2. So watch. Assuming I was able to calculate for the value of I1, then from this node, we know that the total current entering here, when it gets here, it will split into two. The first one is 1, the second one is 2. So IT from Kirchhoff's current law is equal to I1 plus what? I2. Now, if I know I1, I can find I2 by subtracting this from this. So IT minus I1 is equal to I2. We will apply this when we start solving questions, okay? If I also calculated for the second current, which is the current passing through branch 2, which is called I2, I can subtract the result from the total current if I have it to find what? I1. I hope you got that concept. Now, let us fix some values here and see the result we are going to get. Now, let's find the current through the 7 ohms resistor, okay, which is through branch 1. From current divider rule, we learned that I1, the one I am looking for, should be equal to take the total current, IT, multiply the result by the what? Opposite resistor, not this one. The one that is opposite to what? This. Now the opposite resistor is what? 4. Divide the result by 4 plus 7. Now we know IT to be equal to what? 15 times 4, all divided by 4 plus what? 7. Now when you punch this on the calculator, we have our I1 equals 5.45 when you run to what? 2 decimal place. So 5.45 what? Amps. In the same way, if I want to find I2, which is current 2, I can use the same formula. I2 equals the total current, which is 15, multiplied by second resistor value, which is opposite to that one. So we take what? 7. Divide the result by 4 plus 7. Now when you punch this on your calculator, the result is 9.51 amps. Now, the other way you can also solve this one is by subtracting this result from the 15 to get what? Your I2. You don't need to use this formula. So I can say that I2 equals IT minus what? I1, which is the same as I2 equals 15 minus 5.45, which will give us this result. Okay, so once you subtract, you can run to 2 decimal place. But usually, when you are subtracting, when you are working on this, work with 4 decimal place. Since you'll be using the answer to work other calculations, work with 4 decimal place. Okay, so later on, then you run the final answer. You can run to 2 decimal or 1 decimal place, depending on what you want to do. Okay, another thing I want you to know is that I am dealing with resistive circuit, okay? We can also apply this theorem with inductive circuit and capacitive circuit. There are some slight difference with, I think, the inductive, but I don't think I will be talking about that. In case my viewers, if you want me to do that, you can let me know. I will think about it and do it. Now, in the beginning, I will explain this one. And I told you that when you want the first current, you do this. When you want the second, why this? So I want us to find out the reason why the formula behaves like this. Once we are done proving, then we solve this question and we will call it a day, okay? Now watch. From Kirchhoff's current law, we know that IT will enter here, split into two, one will pass here, one will pass here. So let's say our IT equal to the summation of these two, okay? I1 plus I2. Very good. Now let's go back to Ohm's law. From Ohm's law, we know that V is equal to IR. Now I am interested in I1 and I2, so let's make this current the subject of the equation. Once I make this current the subject of the equation, I'm going to get I equals V over what? R. Watch you. Now, I need I1. So let me label this one I1. And then I'll label its resistor R1. The voltage can remain the same since the voltage across the circuit is the same. Then let's write the same formula for this one. Let's assume that I2 equals V over what? R2. Do we all understand? Now let's label this one equation star. Then let's label this one equation 1. Let's label this one equation 2. The next thing that we will do is that let's put equation 1 and equation 2 into the equation star, okay? And let's see what will happen. Forget about this diagram, we come back here. Now when we put equation 1 and 2 into equation star, we are getting IT equals V over R1 plus V over what? R2. Do you understand? Because this is I2. So it is representing this one. That's what we have there. Now, let's take LCM here because we have addition, two fractions. So let's take LCM here. Now, when we take LCM, LCM will be R1, R2. So let me put it here. Now, R1 will go here. That means it will cancel this one. It will be left with what? R2. Use this R2 to multiply the V at the top. So we have V times what? R2 plus R2 will cancel this one. It will be left with R1. Use it to multiply this. So we have V R1. In our next step, we can factorize the V. Okay, so we have IT equals V outside. Let me factorize starting with R1, okay? So R1 plus what? R2 is still the same thing, okay? It's still the same. When I multiply, I'll get the same result. Divide this by what? R1, R2. The next step is, let us make this V the subject. Do you know why? Because in equation 1 and 2, I have V here. And I'll come back to equation 1 and 2. So let us make V the subject here. If I want to make this V the subject, so for those of you who have math issues, so look at this very carefully. I'll divide here by what? 1. To those of you who can do it, you know what to do. And I'll cross multiply. This side will multiply this one will multiply this function. Now when we do that, what are we going to get? We are getting IT times R1, R2, okay, equal to 1 times this function is giving us V into bracket R1 plus R2. Now, I want to make V the subject, so I'll divide both sides by this function to remove it. So when I divide here by R1 plus R2, I'm supposed to do this in the next step. And then I'll divide here by what? R1 plus R2. We all know this will cancel this. We are left with what? V. So our equation becomes V equals IT times R1 times R2, all divided by R1 plus what? R2. I hope we all understand. Now from here, let's label this equation 3. Now let's go back to the original equation. Let's take the first one, equation 1. Wherever you see V, put equation 3. And let's see what will happen. So from equation 1, we have our I1 equals V, which stands for everything we have here. So I'll write it as my IT R1 R2 all over what? R1 plus R2. This represents the V. Then divided by what? Our R1, which is here. Another way you can put this equation is to do it this way. You have your IT R1 R2 all over R1 plus R2 divided by this R1, which I have here. The next thing I'll do is that I will reciprocate the R1 there. So our I1 becomes what? IT R1 R2 divided by R1 plus R2 times 1 over R1. Do we all get it now? Now this will cancel this. So we are done. So now the equation becomes I1 equals IT times R2 all divided by R1 plus what? R2. So now we have been able to prove the reason why they are saying that when you are finding the current in branch 1, you need this formula. Now this formula is equal to the original we wrote. Okay, so I've cleaned that one, so I think you can go back and look at the original equation. You see that it is the same. In the same way, when you fix this voltage into equation 2, you will generate the equation that we wrote for what? I2, finding the current in the branch 2. Okay, so this explains the reason why the current divider rule behaves like this. So I hope you understand. Now, the next thing we will do is that I'll put some values in there and then we will solve. And then I'll call it a day for this one. From this example, it is similar to this, and I'm going to apply current divider. That's why I want to take this example, because there is something I need to teach you. This question says we should find the current through this one. So let us label it. I am not using voltage here because I'm just giving you a straight direct current that is entering the individual branches. Okay, when we are doing complex questions, I'll change this to a voltage source. Then we find the current before we use it to do the calculation. Now watch, this current is 10 amps. Let's call it I1. So I1 will be here. It will pass through this 2 ohm resistor, and then a portion will drop to this junction or this branch. Let's label this side I2. A portion will pass through the 3 ohm resistor. Let's label it I3. Let's label this node. Once I3 gets to this node, it will split into 2. Let's label this side I4. And finally, this side I5. Do we understand? Now note here, at this junction, I1 has finished supplying. It is the supply current. It has finished supplying. It will supply I2 and I3. Now, at this junction, which is called this node, I3 becomes the supply current. So put that in mind. It is not this one. I3 becomes the supply. It will supply I4 and I5. So the value of I3 will split into 2. One will pass through this branch, and the last one will pass through the last branch. Now, let us find the value of I2 passing through the 8 ohm resistor. In this circuit, which we did, the first calculation, we realized that we had only 2 branches. And in the branches, we took the opposite resistive value to do the calculation. Now, this 8 ohm, which one is the opposite value? Which value will you use here to help you formulate the formula for the current divider rule. Now let me teach you a trick. We need to resolve. Everyone knows that. But because the current source is on the left side, you will resolve from the right side. What it means is that I need to reduce these resistive values until I get here, so that these 8 ohms will have its opposite resistor to be only the value that will be here. So how do we resolve? This and this, the 4 ohm and the 5 ohms here are parallel because they are not having the same current passing through. So because they are parallel, we need to resolve it. We need to join them together until we get here. Now this and this will be parallel and it will be in series with this one. I will break the equation down for you to understand. So the first thing, let me label it RP1, standing for R parallel 1. So RP1 is equal to, now for a parallel circuit, you know that if these two are parallel to each other, if you want to find the total resistance, you multiply them and you divide by the addition of the same values. Okay, you can, I think, I will not talk about that, you can read about that. So it means that we have 5 times 4 all divided by what? 5 plus 4. Okay, now this result will be in series with this, but not to confuse you, let me maintain this one and solve. So once we multiply this one, we will get a certain value. Now, when we divide this, this will give us 20/9, which is giving us 2.22. You let me do it for decimal place. Okay, I want to explain something. If not, I wanted to add the result to that. Now, after you calculate this one, you could see that this and this will behave like this, and it will be in series with the 3 ohms. Okay, so if it is in series with the 3 ohms, then I can add this and this to join them together so that it will be opposite to what? The 8 ohm resistor. That is what we will use to do the calculation. So if we add the 3, what are we going to get? I was supposed to add it here, but because I am explaining, that's why I drew a new diagram. I don't need to draw that. I just need to go straight. Good. So now when we add this and this, which are in series, the reason is that now the current passing here is what? I2. This is I1. So I3 will pass through this 3 ohm and the same time passing through this junction. That is why we have to join them together. So when we join them together, we have what? 5.5 ohms. So let me put it here. So R series 1 is going to give us what? 3 plus 2.2222 what? Ohm, which is approximately 5.22 what? Ohms. Now this value, when we redraw the circuit, what are we going to get? Now let me redraw the circuit. Now watch, after redrawing the circuit, look at the way it is behaving. Now this 8 ohms has the opposite resistor to be what? 5.22. So you could see that in the original equation, I can't use 3. I need to resolve these two. 1, 2, 3. I need to resolve these 3 resistors so that I can use current divider rule to find the current on the branch, or on this one, or on this branch. So now that we are here, we can solve. Now I can apply the current divider rule by saying that I need the current on this junction. So let me write it down. I2 equals what? What is the opposite resistor? 5.22. So I will take the total current that is supplying this junction. It is I1. This I1 is supplying what? This node. So it is the total, the supply current that is coming. So you use it to multiply. Now, multiply by the opposite, not the one that I2 is passing through. So we pick our 5.22 divided by 8 plus what? Our 5.22. Do you understand now? So I've applied the current divider rule we initially did here. So now this current, the value is what? 10. Let me clean it and put it there. So I put my 10 here. So let me use the 4 decimal place here. Good. So now when you use 4 decimal place, okay, so now when we multiply, we are getting 3.95 arms. If I run to 2 decimal place, and if I run to the nearest whole number, I'm going to get what? 4 arms. So you see, I applied current divider rule here, but before I was able to do it, I have to resolve the resistors that are distracting me. Okay, 1, 2, 3. I need to join them together. So this and this is parallel and in series with this. So in the calculation from the beginning, I didn't have to draw this circuit, this particular one. I just need to draw this one. So I can clean this circuit, clean this side, okay, and add my what? Plus 3 coming from here. Okay, so once I add my plus 3, the result will be what? 5.222. So straightforward, I can just draw this circuit if you want to show it, and then calculate for the current passing through this side. If you want the current passing through here, you just take this value, subtract it from 10, from I1, you will get I3. Now note, they can ask you to find the current that is passing through the 4 ohm and the 5 ohm. Now, if that happens, because you already know the value of I3, note that I3 becomes the source supplying this node. So you just use the same current divider rule. If I want I4, I will just take I3 to multiply this 4 ohm resistor, divide by 4 plus 5. I will get the value that is passing. I can subtract the answer from this to get the I5. Or you can also say that I5 equals the supply current, which is I3, times the opposite resistor 5 ohm divided by 4 plus 5. And you will get the current passing through here without using the Kirchhoff's current. So this is how we apply current divider rule when we are dealing with network analysis or network theorems. Now, know that there are certain circuits that you can't apply the current divider rule. You have to use other ways because the circuit is too complex. So that is why we have what we call the nodal analysis, we have the mesh analysis, we have the Thevenin's theorem, and then we also have the superposition theorem. I'm going to talk about all of these topics as we progress. So thank you very much for joining me here. I hope this was very useful. All right, so if this has been very useful to you, you can subscribe to this channel for more updates. My name is Daniel. You can also share with your friends, share out there if this was helpful. And we are going to talk about voltage divider rule in our next video. See you in the next one.